This is related to thermodynamics of horizons and how you derive the temperature associated with horizon, etc. I have discussed in the last lecture. At the end of the last lecture, I also pointed out a very curious relationship between the gravitational dynamics and the horizon thermodynamics. What we pointed out was that if you look at a solution to Einstein's equation, let us say, which has a horizon at r is equal to a, and you think of infinitesimal virtual displacements of this horizon, that equation, the Einstein's field equation, when evaluated on the horizon, reduces to an identity like TdS equal to E plus TdV. I did not elaborate on that because it is not textbook material, but I just thought you should know that there is this curious relation. Today I want to discuss quite a bit of aspects of the dynamics of gravity, all of which has connections with what I said in the last lecture, but the connections will only be apparent later on. But the relations by themselves are quite interesting and curious, so I will have to spend some time deriving them further. That is what I am going to do. So to begin with, let us, as usual, start in this advanced general relativity course with classical mechanics. So in classical mechanics, we have an action which you would have normally written as integral over dt of a Lagrangian, which let us say depends on q and q. Bear with me, things will become non-trivial pretty soon. Now, in classical mechanics, what we do is that you vary this action and you look at delta A, and you will find that by standard procedure, delta A is going to be given by dt. Then you have the Eulerian term, which is dl by dq minus, I'll write it as dp by dt delta q. Then you have this extra term which you have thrown away, or will usually throw away, which is integral over dt of d by dt of p delta q. This is standard stuff, and the p here is merely a symbol. P is a function of q and q dot. It is not momentum in the sense of Hamilton's mechanics, and it is defined as dl by dq dot. Okay, this is standard stuff. Up to this point, I haven't said anything about what kind of variations we are studying. The usual assumption at this stage is that there are two kinds of variations you can think of. The first kind of variation, you are going from some T1 to T2, and you are going to fix things at T1 and T2. The first kind of variation is when you fix Q at the endpoints. So you say that delta Q vanishes at the endpoint. If delta Q vanishes at the endpoints, when you integrate this, you get a P delta Q term there, and that delta Q you throw away. And then if delta A has to vanish for variations in which Q is fixed at the endpoints, then this part should vanish. That gives you the Eulerian equation solution. And it is also obvious from here that if your Lagrangian depends on q and q dot, the highest time derivative you will have is q double dot, the old standard step. There is also another kind of variation which you can use in action principle, which is, especially in field theory, it is very useful and powerful. You can think of the variations of action on shell. That is, you look at what delta A will be when the equations of motion are satisfied. You first derive the equation of motion and then plug it back in. Then this term will completely vanish, and what you are left with is just P delta Q at the endpoints. So the derivative of the action treated as a function of the endpoint coordinates Q and T, dA by dQ, will give you the canonical momentum. Of course, this is the basis of Hamilton-Jacobi theory. You can also find that if A is treated as a function of the endpoint time, then ds by dt is minus h. So you have ds by dt, dA by dt is equal to minus h, and dA by dq equal to p, and when you combine them together, you get the Hamilton-Jacobi equation. So that is the second kind of variation. So the action itself, even without using the Lagrangian, if you know the variation of the action and the contribution coming from the endpoint, you can identify the moment. And this works in field theory as well. Now, if you want to study any other system, let us say gravity, and you want to get the field equations, you might as well start from the field equations and postulate it, but most of the time you would like to start with an action principle. So in gravity, what one would like to have is an action which in the same sort of way, since we are discussing field theory, you will have a d4x, let us say in 4 dimension, root minus g times a Lagrangian L, which depends, the dynamical variable we will think of as the metric and the first derivatives of the metric, which is just a generalization of this. Then we will vary this and you want to get the equation solution. When you want to make a choice for the Lagrangian, like in electromagnetism or in any other field theory, you would like to impose all the symmetries you want on the equations on the Lagrangian. There is a bit of a subtlety here which I will come back to, but for the moment let us assume that we want the Lagrangian to have the same symmetries as the equations of motion. In which case we would like to write down for L an expression built out of the metric and its first derivatives, which is a scalar. Now we all know that such a scalar doesn't exist except for a trivial constant. The usual proof for that goes as follows, that you take any event and at that event I can choose a local inertial frame. If you take the local inertial frame, then the delta G can be tried off for gammas, the Christoffel symbols, and the Christoffel symbols vanish and the metric becomes a constant, so Lagrangian becomes a constant. So if it is a scalar, it is going to be a constant everywhere, and hence you cannot have such a scalar. This is slightly unsatisfactory for the following reason, because what is involved here is the variation of the action, not just the variation of the Lagrangian. I mean, I know that the result is true, so you can argue like this and get away with it, but if you want to be very formal about it, you cannot have a local inertial frame over a region, and it is the integral over that region which you are asking, so you need to rethink it a little bit. But it is very easy for you to convince yourself by just the exhaustion method that if you take all the quadratic terms which can be built out of Christoffel symbols. So the Christoffel symbols are equivalent to using del G. So you take the Christoffel symbol, there is a gamma ABC and a gamma ijk. Contract them on all the 6 indices in whichever possible way you want, and then ask whether you can get a scalar, and the answer is no. So by explicit construction, you know that a scalar of this kind doesn't exist. So what do you do? Now at this stage there are various possibilities. The first possibility, and all of them will lead to the central theme of today's talk, which is surface terms in the actions and the role they play. The first thing is you go back and ask whether the argument is watertight. What I really needed was the field equations to be generally covariant. Is it possible that I have a Lagrangian which is not generally covariant, but its variation is generally covariant? That is actually possible, because you can write down a Lagrangian such that when you vary it, the variation is the generally covariant term plus a surface term. And just as the endpoints here are being kept as constant, you can arrange the Lagrangian in such a way that the surface term remains constant when you are varying. Therefore, your equations of motion will turn out to be generally covariant. That is one way out. But then your Lagrangian is not generally covariant. And the price you pay is that if you ever want to think of a quantum theory of gravity, or this is generally applicable, a quantum theory, using this action principle as exponential I over h cross for a given configuration, configurations which are not classical will pick up contributions which does not preserve the symmetry which you want. So that is probably not a nice thing, but anyway nobody has constructed a quantum theory of gravity, so it is not clear how much of a validity you can give to that argument. Of course it would be nice if you can actually write down a Lagrangian, which is generally covariant. Now there is only one scalar which you can build up other than a constant, which will turn out to be a cosmological constant, but I won't go into that. Other than that, the only constant which you can have is the scalar curvature. So the action which you can think of is this. So this is the usual Hilbert-Einstein action which you write down. And this R we know involves second derivatives of the metric, first derivatives of the metric, and G. However, it depends on the second derivatives of metric only linearly. Therefore, one of the terms can be separated into a boundary term. This is the usual argument. And then that boundary term can be thrown out. This argument, as presented like this, even in books like Landau and Lipschitz, is simply wrong. I mean, there is no nicely tempered way of saying it. The argument is wrong. And I'll tell you why the argument is wrong. The argument taken by itself is not wrong. If you only want to derive the equations of motion, you are free to choose the kind of variation I want to choose. And you can say, oh, I am going to choose a variation in which the boundary term vanishes. But it is not in conformity with the usual analysis which we do. Let me explain why. Now suppose instead of this Lagrangian, just to take that analogy further, suppose I had an action which is integral over dt of L, which depends on, let us say, q double dot, q dot, and q. And in particular, let us assume that it has a structure which is linear in q double dot. So you have to take d by dt of some function which depends only on q dot and q, and let us say plus some constant times q double dot. Okay, I'm just mimicking gravity with classical mechanics. So when you integrate this out, you get the first term, which is your, I will call it A quadratic, which has only the terms which are quadratic in q dot, this conventional kind of Lagrangian. Then plus you get an integral over this, so you get lambda q dot at the endpoints t1 and t2. Okay? So the idea now is that when you are varying this action, variation of the A quadratic is going to give you exactly this kind of a structure, and in order to get sensible equations of motion from there, you have to assume delta q is 0. So you have to now assume that both delta q and delta q dot vanishes at the end. So this is why I said actions of this kind are not in conformity with it. There is a reason why you can get away in gravity. I will come back to that. So you have to assume both delta q and delta q dot to be 0 at the end point to get equations of sensible equations of motion out of it. But what is wrong with that? Well, there are two things which are wrong with it, and both have quantum mechanical origin in it. But as I said, the action principle, if you are only interested in classical equations of motion, then you don't even have to go to action principle. You might as well write down the equations of motion and be done with it. The whole idea was that the action is a window to the quantum theory. And if it is a window to the quantum theory, you need an action which you can use in a path integral. In a path integral, first of all, it is very obvious that once a dynamical variable has been chosen, if q dot is like the momentum, you are now saying that at the end point you give me both the position and momentum of a particle. This people don't like in quantum mechanics for very good reasons. The second and the formal reason is that normally you would have liked, when you are doing path integral, the actions to have a transitive property. That is, if you look at the action between endpoint variations, I mean endpoints chosen by 3 and 1, you would have liked it to be decomposed. This is equality in the sense of decomposition. 3 to 2 plus action from 2 to 1. So when you are summing over various paths, there are paths which will cut that midpoint T2. You are going from T1 to T2 to T3. At T is equal to T2, you want the paths to be continuous, but nobody said the paths have to be smooth. And in fact, most of the paths will not be smooth. So you cannot sort of say that both Q and Q dot for that path I am going to fix at the in-between points. So because of these two reasons, it is not very obvious that you can do this and carry on with it. However, the surprising thing is, there exists a subset of actions of this form, which involves L of Q double dot, Q dot and Q, for which it works. So I want to talk about those actions. These are the actions which are obtained by a Lagrangian of a very special structure. I will denote them as LP, the meaning will be clear in a moment. You start with a standard Lagrangian, which I will call LQ, which depends on, let us say, Q and Q dot. And then you subtract from it d by dt of QP. So I'll write it in full for a moment. This is just what we have called P. Okay, and this is LQ. So what have we done? This depends only on Q and Q dot. This P depends on Q dot and Q. So when you do a derivative of that, you pick up Q double dot. So this Lagrangian LP will depend on Q double dot, Q dot and Q. Now first, just to make clear that everybody understands what is going on, I have added to it a d by dt of some quantity. So you may remember some statement in classical mechanics that you can always add a total time derivative to a Lagrangian and nothing will change. That is true, but that statement would have also said that it is the total time derivative of a function which depends on Q and T. If to this Lagrangian L here, I have added a term which is df by dt, where f depends only on Q and T, the endpoint contributions would be f at Q1 T1 minus f at Q2 T2. Since I am keeping the endpoint Q's fixed, nothing will happen. But you are not allowed to add a Q dot dependent term and still hope the same equations of motion to come through. Nevertheless, if you vary this, but keep delta P fixed at the endpoints, you get exactly the same equations of motion. That is because if you look at the action which comes from this, which I have called AP, and you look at the variation of that, you will first pick up the variation of AQ, which is this. Then you will pick up minus delta of PQ evaluated at the endpoint. So delta of AQ we know has the structure which we have worked out. It has an integral over dt of the Euler function, this entire bracket that we call the Euler function, delta Q. This gives you the equations of motion. Then I have plus P delta Q at the endpoints. Then I am subtracting from it this, which is minus P delta Q minus Q delta P on 2 on 2. So these two things nicely cancel out, leaving you with dt, the standard Euler function delta Q minus Q delta P. Now the argument is that I am going to study variations in which the momenta are fixed at the endpoints, not coordinates. Therefore, this vanishes, and if delta A has to vanish for all delta Q in between, then E should vanish. Okay? So, if you know canonical transformation, you can immediately see this in the Hamiltonian picture. You are just going from Q representation to the P representation, and this d by dt of PQ, which I wrote down here, is just a canonical transformation. But since we are talking about it in the Lagrangian mechanics language, you have to actually explicitly work it out. Your P is not an independent variable, it's a function of Q and Q dot. But of course the mathematics goes through. So there exists a very special class of Lagrangians which has the following structure, and these Lagrangians will allow you to obtain second order differential equations, because this only involves the highest derivative is only second order in time, even though they themselves contain second derivatives of the dynamical wave. You would have expected a third order differential equation or a higher order, but that will not happen. You will get the second order equations, and you can think of it as with a delta P fixed. Now in quantum theory, this has a very nice interpretation. If you try to do path integrals, you can use the standard Lagrangian LQ, and you will write the kernel, path integral kernel. We have done it several times with, let us say, Q2 T2, Q1 T1, This we would have written as summation over all paths exponential I times the Lagrangian, the standard Q Lagrangian, the subscript is just the standard thermodynamic notation. This says Q is fixed, LP means P is fixed. So the LQ dt, this is how we would have got that. Now suppose you want to know the propagator in the momentum space. That is, I want to know not the Q2 T2 kind of a structure, I want to know what is P2 T2 starting from P1 T1. That is, I am asking what is the probability amplitude that a particle which originally had a momentum P1 at T1 ends up having a momentum P2 at T2. You can write a path integral for that too. That is because once you know this K, it is just a Fourier transform. So the Fourier transform will involve exponential I, a variable P2 Q2 and a P1 Q1 at the two endpoints, which I can plug in with this. So that is given exactly by the path integral, which has this exponential I integral LQ minus d by dt of PQ dt. When you integrate this, you get a PQ term at the endpoints. You write it as P2 Q2 minus P1 Q1. And when you are doing the summation, you just include the summation at the endpoints as well. Here when you are summing, you take all the paths which has a Q1 T1 fixed and Q2 T2 fixed. But when you are doing the sum here, you let Q1 and Q2 also to vary. That is, you integrate through those endpoints as well. But you keep the parameters P2 and P1 fixed. So this is nothing but your LP. Okay? So if you think of it as quantum mechanically and you say that I want the transition amplitude between a state with momentum P1 to a momentum P2, the natural path integral you would have constructed, though it is never sort of discussed in textbooks, people do discuss it in terms of Fourier transform. After all, we know that the wave function's Fourier transform gives you the momentum space representation. But at the level of path integral, if you want to modify the Lagrangian, this is the modification you would have done. So the Lagrangians which has this particular structure are very special, and they represent the same theory in the momentum space. Okay? And they will have this advantage that even though the Lagrangian depends on the second derivatives of the dynamical variable, the field equations will still be of the second order. Now the question is, what happens in gravity? Yeah.
Why would you expect the field equations to have higher derivatives?
In general?
Yes.
Yeah, if your Lagrangian had Q double dot, then if you do the variation in the standard way, you will end up getting a higher order derivative. Because you have to vary that delta Q double dot term as well.
Time.
Sorry?
Higher time derivative.
Yeah, higher time derivative. Which when you translate into relativistic theories, it will have higher time and higher space. Higher space never bothers anyone because as far as evolution concerned, higher space just means you need more spatial derivatives at the initial condition. But higher time requires more conditions, and it also has other instabilities, etc.
So if you now say R, the Einstein reproduction is the LQ, can you then go back and construct an LP for the relativity?
That is the lecture. Okay, yeah. So we have now this much of structure, and now let us look at the Einstein-Hilbert action. So you want to start with the expression for R, which is the Lagrangian. Root minus I have an ambivalent attitude towards root minus. Sometimes I'll keep and sometimes I'll remove, but right now I'm going to just keep removing. So let us look at R. And I want to write R in a particular way. I will write it as Q A B C D R A B C D, and just to get notations out of the way, I could have also written this as Q A B C D R A B C. This is the Riemann-Christoffel tensor or the curvature tensor, and written with this index up and these three index down, it is nice because it can be written entirely in terms of Christoffel symbols. The G's will not appear in that, so it's a nice representation. This quantity is another tensor, fourth rank tensor. In this particular case, it is constructed just out of the metric. And in this contracted form, I have two indices up and two indices down. And the convenience in the case of Riemann-Christoffel tensor is that I don't have to worry about which is placed where. We know that it is antisymmetric in these two, it is antisymmetric in these two, and it is symmetric under pair exchange. Okay? This has exactly the same symmetries of the Riemann-Christoffel tensor. Now we will study very general structures of with having these symmetries, but for the moment let us stick to Einstein's theory. So in Einstein's theory, this is very simple. The QABCD is just what is known as the determinant tensor. So QCDAB will be, I think that is a half, but you can refer to my notes for factors, etc. Delta C, delta A, Kronecker deltas, dB minus delta D A delta C B. So this is, again, in case you have forgotten your tensor analysis, this is essentially built out of a determinant. You take a 2 by 2 determinant. Each of the entries are Kronecker deltas. So this is just one diagonal minus the other diagonal. So you can naturally generalize it to any number of dimensions. You can take a determinant of a matrix in which every entry is a Kronecker delta and you can compute its determinant. And you will get a much more horrible structure than that. But it will only involve ones and minus ones and zeros kind of a thing. I mean, depending on which terms which you are picking up. Okay? So that means the ordinary derivative of this vanishes. And if you rise and lower them to get these quantities, you will end up getting the metric tensor. But even with metric tensor, since metric tensor is covariantly conserved, you have the identity that Q ABCD's divergence vanishes. You can also explicitly verify in this case, it's very straightforward, that it has exactly all the symmetries of the Riemann tensor, the algebraic symmetries of the Riemann tensor. Therefore, with this and the symmetries of the Riemann tensor, it is divergence free in all the indices. So essentially, I want to think of Lagrangians built from the curvature by this structure, where this Q has all the symmetries of the Riemann curvature tensor, and it is divergence free in all the indices. Now, what can it depend on? In this particular case, we are going to say it depends only on the metric tensor. So if you say that, this is the unique choice. Again, that is something which you can prove. There are no other tensors you can construct out of a metric which has this property. So this is what Einstein's Lagrangian is like. Now obviously the reason I am writing it in this form is because it allows me to generalize very easily to a much wider class of cases. So now I want to study this in slightly greater detail. So let us look at what we have here. So let me first give you an orientation as to what is going to happen, and then I will write down the result. What do we have here? This R has this structure, very formally suppressing the indices Q and the curvature tensor. So I shouldn't probably even put an equal to sign. This has the structure like this, right? And this in turn is Q. We know that R has this structure which is D gamma plus gamma gamma. So this is what you have. Therefore, just to see ahead what is going to happen, take this first term and write it as D of Q gamma minus gamma dq, which you can do. I'm just pulling the total thing. Then you have a term which is plus Q gamma gamma. All indices suppress it. Now you go and use this condition. What this condition tells you is that you have a dq plus a whole lot of gamma q equal to 0. Therefore, the dq, I mean, if you expand out the covariant derivative, this is the structure which will emerge. So, this dq can be traded off for minus gamma q from that condition. So, you plug that into this. So, you will find that this is also of the form q gamma gamma, which is exactly that is. Therefore, this whole structure will become del of q gamma plus q gamma gamma. Okay? I will put in the indices in a minute. So you know that any theory of this kind in which q satisfies the divergence condition is reducible to this form. So there is an ordinary derivative of a q times gamma term here, which when you integrate out, and here is where I should have put in an r root minus g there, and that root minus g would have carried through everywhere, and you would have a root minus g there. So the integral over d4x of that quantity will give you a surface term from it. And this term, when q depends only on the metric, is quadratic in the first derivatives of the metric. Okay? So you have a structure here where we have proved, sort of index-free manner, that the r root minus g can be written in a form which is one surface term plus a term which involves quadratic terms in the Christopher symbol. So let me write down these formal expressions for that, which, since I don't want to make a mistake, let me refer to this. So what you can show is that square root of minus gr, when you put all the indices in, can be written as a root minus g L quadratic. This is the second term which involves q and gamma gamma, and there I separate out the root minus g, that is more convenient, plus an L SUR surface, in which I have not separated out the root minus g because I just want to think of it as ordinary derivative of something integrated over d4x. So the explicit expressions for them are as follows. The L quad times root minus g, or L quad itself, is 2 times q a b c d gamma a k, let us say d gamma k b and c. So of course this just depends on g's, and you can work that through, and that will give you an expression which is GAB comma ij a comma j I b minus gamma I AB gamma J I J. It's worth writing it down once. So you have a term which is just the quadratic part of it, which has this structure, and then there is a surface term. L surface is a total divergence. This will be twice dc root minus g q a b c d gamma a b d. This can be simplified quite a bit and written in very many different ways. And the way I would like to write it down, let me use the blackboard on top. The way I would like to write down that term is L surface is dc of root minus g times a vector vc. Well, I shouldn't say vector, 4-component object vc. It is not a vector, where vc can be written as GAB gamma ABC minus GCB gamma B, let us say GG. Okay. Again, if you remember your tensor analysis, you know that there are expressions for GAB contracted with gamma AB and this JJ contracted with 1 int x3 in terms of derivatives of the matrix. If you use all of them, this will turn out to be minus 1 by g, not root g, d, let us say b of g, gbc. That leaves the say free int x as c. Okay. Yeah, I just want to make sure I haven't written the wrong expression. Yes, that is correct. So this is one place where the determinant of g itself appears rather than the square root, but you can of course write it with an extra square root symbol. But this is it. So this is the way your r root minus g separates out. So just to go back here, the root minus g times r has these two terms. There is a quadratic term which is quadratic in the Christoffel symbols and therefore it is quadratic in the first derivatives of the matrix. And then there is another term, surface term, which is of this structure. Now it turns out, and that I will not prove, but it is very straightforward and it is done in the notes, that the separation written in terms of this Q holds for all theories in which this Q ABCD has the symmetries of the Riemann-Christoffel tensor and it is divergence free in all the derivatives, all the indices. In particular, it does not depend on the fact that it is built only out of metric. So you can have much more complicated Q ABCDs built out of, let us say, the curvature tensor and the metric, which satisfies these properties, and this result will still hold. And in all those cases, you can separate it out like this. Of course, once you do that, in this, you will have two gammas, but here you may have curvature tensor. So it is no longer, you cannot no longer say that it is quadratic in the gammas. Those are special properties of the Einstein theory which we will discuss, but in general, this is true. Now you can also see, this is in answer to your question, that if you look at the quadratic term and this term, you can already see it happening. If I look at the derivative of this with respect to the derivative of the metric tensor, so let me write that down first. What do we expect if it is a momentum space integral? So since I have wiped it out, let me again remind you that the LP was supposed to be LQ minus d by dt of Q dl by dq dot. But this is of course Q. So in our case, what you would have expected is that this structure should change into L quadratic, and there is a extra root minus g which I have to be careful. So since I have not put the root minus g in that, it is L quadratic minus dA d by dt will become a general dA. Then there is some metric which I can take to be, let us say, gik dl quadratic root minus g, though it doesn't matter, with respect to dA of gik. So this is, I claim these are identical in structure. So if you think of L quadratic, the LQ as root minus G L quadratic, then what you have here is that quantity, derivative of that with respect to Q dot, so to speak. The Q's for us are the metric tensor, Q dots are the derivatives of the metric tensor, and this in general defines the momentum density. And then the Q again appears here, just as this Q. And this is what is the code. Therefore, this quantity, this second quantity which we have, this should be the L surface. It turns out that this is true. Now, this is a beautiful exercise in index gymnastics if you want to try it out. You start with the expression for that, take this derivative, multiply by this, and then take the derivative and show that this is actually that root minus GVC. It's well worth a try. However, after having done that, I found a very clever way of doing it using just scaling arguments, which is given in the notes. So if you read that, then you will find that there is an elementary proof using scaling arguments. But this relation is sort of made clear if you think of this as gammas. So what we are doing is that we are taking the derivative of the quadratic Lagrangian with respect to gammas. So the quadratic Lagrangian is here. You take the derivative of that with respect to gammas, you will essentially pick up Q times gammas. Then you contract with the G, and the surface term should be Q times gamma. So it is fine, but of course you have the devil is in the details, and you have to make sure that all the indices match, etc., and which you can show. So the Einstein's theory has this extremely peculiar feature that the full Lagrangian of the theory, which is root minus G times R, can not only be separated into a surface term and a bulk term, but the surface and the bulk terms are related in a very peculiar way. For the want of a better terminology, I called it holographic, but it has nothing to do with the holography which you hear in string theory. So you have this structure, and I should add a little bit of history here. This is especially for students, and one of the lunches we were discussing about, I think you mentioned it, that somebody said that, oh, this can't be true because if it is true, somebody would have discovered it before. There was an argument about some discussion and someone supposed to have said that. That is completely wrong in physics. So you may think that a thing like Einstein-Hilbert action, which has been looked at for decades and has appeared in every textbook written by very eminent people, you will find this in print. In first place, you will find this in print is my book, problem book on gravitation and problem book in cosmology and astrophysics. I do not know of reference earlier than that. We had checked this with several relativists, and it doesn't seem to have been noticed. Okay. We stumbled on this in a very interesting way, which is also worth mentioning, essentially for students. This was first discovered by me and Donald Lindenberg. And we were looking at the problem of analyzing galaxies in the local group. So there are galaxies, now we are switching gears, there are galaxies flying about in the sky, and what astronomers usually measure is the one radial velocity and two transverse position. They can measure them very well because radial velocity from Doppler shift and transverse position by looking at the sky. You ask them to give you the transverse velocity or radial position, the error bars are huge. So we wanted to construct an action principle for studying the dynamics of the local group, in which the endpoints will be neither coordinates or momenta which will be fixed, but it will be a mixed condition. That in one direction we will fix the momenta or the velocity, and in the other two directions we want to fix the coordinates. So we wanted to know what Lagrangian I should put so that you can minimize it in the computer. When you throw it in and let the computer do the minimum and then track back the trajectories and back in time, etc., etc. That was the idea. So we found that the Lagrangian which I should use is that LP Lagrangian, which has this form. And then we also realized that in computer it become a bit problematic because it involves second derivatives. So we realized that all these will have second derivatives. So just as a curiosity, we said, okay, let us see. We know one Lagrangian which has second derivatives in it, which is R root minus E. Let us see whether it has this structure. And lo and behold, it has this structure. This is very close to this exists, for example, in Tolman's book in Relativity. It exists in Fock's book in Relativity. But nowhere has this been explicitly written down. And I think this is an important relation. That is why I am spending so much of time on it. So you have this relation. And now, if you think of variation of Einstein action in order to obtain the equations of motion, you have a completely alternative framework. You can say that I will work with R root minus G, I will keep the surface term, but I will interpret Einstein's theory in the momentum space. So the things which I am going to fix at the endpoint are going to be these quantities, not the GIK. And then I have a very good variational principle. And this is largely unexplored terrain, mainly because of mathematical difficulties. One can, for example, show that this is actually the canonically defined momentum density from the quadratic expression. And those sort of things you can do. But what kind of theory will emerge out of it, etc., is largely unexplored. But I am not going to go into that. Now if I want to take up another point.
Let me ask you a question. But this is not going to be a covariant quantity.
It is not going to be a covariant quantity.
So
Full thing will be a covariant quantity.
Covariance if you want to fix this or no? You don't
No, in order to see, you are fixing a metric at the end point. Even that is not a covariant concept, right? So whenever you are fixing at the end points, you choose the region and then you fix. So it is no different from just fixing the metric from the quadratic. It is not, but for every foliation, you will have all the transitivity properties given to you. So that is not an issue. I mean, in a given coordinate system, when you want to implement it, you have to say delta GIK is equal to 0. And what is that GIK? That depends on what coordinates you have chosen. But it is coordinate dependent only to that extent. There is another point which I want to spend some time on. The fact that the Einstein-Hilbert action has an extra term like this is very well known. That is not a surprise. It is only its structure which is the surprising thing. There is a suggestion which was originally due to York and then made very popular by Gibbons and Hawking, that you can add a counter term to Einstein's Hilbert action and thereby eliminate it. Okay? So the idea is that you add to this a term which of course depends on the signature, etc. So let me just make sure the term which I am going to use. The term which you want to add to this is an explicit surface term, which is York, Hawking, Gibbons, which is expressed as, in my notation, minus 2 integral over d3x root x of a quantity called k, where k for me is defined as minus di of n. So let me explain what this means. So the idea is that you have R root minus G, and from that you have the Einstein-Hilbert action, the full action, which would have been integral d4x root minus G capital R over some 4-dimensional volume V. You take the boundary of that volume and you evaluate this quantity on the boundary and add this to that action. Then the claim is that when you do the variation of this total action, that is the original Einstein-Hilbert action plus this counter term, then the surface variation just cancel out, as a result of which you get a well-defined action principle. This is a standard claim, and that claim happens to be true. But many people I have talked to, including experts, sometimes believe that this term just removes the surface term. That is, the Einstein-Hilbert action has this term and this term. Suppose I just eliminate this. then I will have a quadratic term, and the variation of which will give me Einstein's theory. And the general feeling is that this k root h is a nice way of doing it. That happens to be wrong. Okay, so I want to spend some time explaining that, because this is again something which you will not find in textbooks, and the textbooks gives you misleading comments on it. But before that, let me explain what this quantity is. The h is the induced metric on the surface. So if you have a full metric in the space-time and you choose a surface, there is a natural induced metric on that surface, and Ni is the normal to the surface. And if you take Ni, which is the normal to the surface, and from that you construct this object, this is known as the trace of the extrinsic curvature. So if you look at the surface and there is a normal, and you ask how the intrinsic geometry of the surface is determined, that is determined by the metric. But how this surface is embedded in the four-dimensional space depends on how this normal changes. In particular, how this normal changes from place to place. So the derivatives of the normal vector is going to contain information about how it is embedded, and this is called the extrinsic curvature, and the trace of this extrinsic curvature is this k. If you don't want to be bothered with any of this, you can just think of it as a definition. Okay, so this is the quantity which we have. Now the question is, how does it compare with the actual surface term we have written, which is here? So there is a Lagrangian which when you integrate gives you a surface term, and here is another surface term, and I want to compare these two. Okay, so I will do that in slight amount of detail. So in order to do that, let us take a space-time, and I will parameterize the space-time in terms of what is known as the lamps and shift functions. So there is an n square dt square. Then you have plus h mu nu times dx mu plus n mu dt times dx nu plus n mu dt. So you have the original metric G00 is traded out for that. The spatial part of the metric has h mu nu, and then the cross terms dx mu kind of dt dx mu kind of cross terms are essentially parameterized by this. These are called the shift vectors, and this is called the Laps function. Okay, but again that is just a name, and you can write down the metric in this form. So we are looking, just for simplicity, I will look at the t equals constant surface. Okay, so on a t equals constant surface, I will compare these two terms. On a t equals constant surface, your normal vector Ni, I will take it to be minus n delta I0. This n is needed to normalize it, and I am putting this minus sign so that when I take Ni, which is the real vector, this is one form, with my signature it will have a positive outward dimension. Okay. That is again just a convention. So now let us compute this quantity. And I will work this out. So you have two terms. First I have the term which is my surface term, which is given by integral over the volume d4x of dc root minus g vc. This gives me, when I confine myself to a t equals constant surface, integral d3x. This is on this is on a t equals constant. surface, the d3x root minus g times capital V0. Now let us look at the Gibbons-Hawking counter term. That is given by another A surface. Let me call this A surface prime. That quantity is minus 2 integral over d3x of root h. Root h I will write as square root of minus g upon n, so as to make the comparisons easy, times k, and this I can write more easily as minus 2 integral d3x root minus g. This is just algebra. N0k. Okay. So I have these two surface terms, and what I want to compute is the difference between these two. So that is A surface minus A surface prime. So that is given by essentially integral over d3x root minus g V0 plus 2 N0k. This I think is correct. Okay, so let us see, it's just straightforward computation now. So let us look at what is V0. V0 is minus, I have to have that 1 by g. 1 by g is 1 by n square h d, let us say I, of again a g. There are two minus signs in the g which just goes away, so I haven't even written it down. That is n square h g I c. That's correct. So this I will separate out in this. I will just keep the h derivative separate from the other ones. So I have minus, if I take this h out, that h will cancel with this, so I have a first term 1 by n square di of n square gi 0 minus gi 0 of di log h. So there is n square gi 0 I am taking out in the second term. That has a di of h divided by h, which is di of log h. Okay? So this is what V0 is. Then you have the next term which we want, which is the 2k n0. So that is 2k n0. This is going to be minus 2 over n times the k's definition, which is divergence of ni, which is n root h dj of n root h times n superscript a. Okay, this is just expanding out di of ni or dj of nj, 1 over root minus g dj of root minus g nj. That gives you the k with this extra minus sign. This is n city. So you have this expression, and now you want to work this through. So when you do that, again you do the same thing, except that this nj it is better to write in terms of n times the, okay, let me just write down the expression and then explain it to you. Yeah. So this nj comes out from j0 of n0, and the n0 will give me an extra factor of n, and the sign will go away. This is a better way of writing that. Then I again play the same game with this. So I have an n square here and n square here. The structure is very similar to that. So I will end up getting 2 upon n square, if I eliminate the root h, 2 upon n square dj of n square gj0. This is one term. Then I get plus root h derivative with a factor 2 here. So that is equal to 2 times dj gj0 dj of log h. Let us make sure of that. There was an n square and an n square here, and there is a root h, and I just concentrate on root h as separate. So this n square, this term, when it comes out, I get a dj of root h divided by root h. That is half of log. With this factor 2, that gives me exactly this. In the other case, I have this 2. Now you compare these two quantities. We are supposed to add these two terms because we want to obtain. So we have explicitly worked out each of the terms. You want to obtain V0 plus 2n0k. So you take this V0 and you add that to this 2k. So you find that this difference A surface minus A surface prime is given by, when you add them up, you get these two terms nicely cancelling out. And in the other, this is minus, but here is a factor 2. So you end up getting 1 upon n square dj of n square gj0. We are not completely out of woods, except that you need to know what are the components of this gj0. That you can work out from the metric. The g00 for the metric is just 1 by n square. And the g0 alpha for the metric is n alpha by n square. You know the covariant terms of the metric from this, and you can work out the contravariant terms. So in this derivative, you have first a d0 of this term. If that had survived, we would have sunk. That is the whole point. You have a surface term, and if the surface term involves time derivative, you are looking at a constant t surface, and if it involves time derivative of the metric, you are talking about the variations normal to the surface. That should not exist in the surface term. But that goes away because that 1 by n square will cancel with this n square, and it is 1 for that term. So this term, when you add up all this, you are only going to get 1 by n square d alpha of n alpha. This is the final result. Now after this gigantic algebra, let me try to explain what I have done. You started with r root minus g, separated it out into a quadratic term and a surface term. And the surface term involved a vector Vc. Then I gave you another surface term, which was an integral of k root h over the boundary. And I wanted to compare these two surface terms in some restricted sense on a t equals constant surface with a particular parameterization. So I just calculated both these surface terms and I did a subtraction of one from the other, and you end up getting an expression like this. Then you go through the mathematics to simplify that, and you find that the difference between these two can be expressed in this form. Okay? Now, what does this mean? First thing it tells you is that it is not zero. Okay? So, it is not that when you add this k root h term, you eliminate completely the surface term which is present in Einstein's theory. There is an extra residue which is there. And that is important. We will come back to that. Now you consider the variations of these terms. Suppose I look at delta of this and delta of this, and I put a delta here. Okay? The delta of this will involve, first there will be delta of n, then there will be deltas of these, but they are all on the surface. On the surface, since I am fixing the metric, variations of things like delta of n will just vanish. I don't have to care. But what about d alpha of n alpha? Since, remember in my notation, alpha, beta, Greek letters go 1, 2, 3 and Latin letters go 0, 1, 2, 3. So this is just a spatial derivative. So if I am fixing the metric on the t equals constant surface everywhere, I have also fixed its derivatives. So the spatial derivatives do not scale. So the spatial derivatives are also constant on that t is equal to constant surface. Therefore, the delta of this will vanish. So if I specify the metric on the surface and I vary the Einstein's Hilbert action, the delta of either this or delta of this, that is delta of A surface minus delta of A prime surface is 0. They are the same. So even though the actions do not match, for variations which fix the metric on the surface, the changes in that action, the variations, are the same. Now you may say that, well, that is all I need. And in fact, that is the whole argument behind using this k root h in the Einstein-Hilbert action. You take Einstein's r root minus g, add to it this k, 2k root h term, and then you vary it. When you vary in the surface term, it is as though you are varying the original surface term. So the variation of the A surface in Einstein's theory is precisely cancelled by the variation of the counter term k root h. But the terms themselves do not cancel. Now, is it satisfactory? For most purposes, yes. But there are a few things which you should know. So the first point was that I told you that whenever you vary a dynamical theory, there are two kinds of variations. One variation is where you fix things on the surface and you find equations of motion. Second is the on-shell variation, where you impose the equations of motion and then you ask what the variation in the boundary tells me. The variation in the boundary will tell you the canonical momentum of the theory. Now, if the variations at the boundary has some dependence on delta G alpha beta, which is different for these two, the canonical momenta which you are going to define for the theory are different. So, even though in order to get the equations of motion it is fine, if you are using it for any other purpose, there are going to be differences whether you are using this or whether you are using this. Okay? And that is the purpose of going through this whole exercise in order to point out to you that they are not identical and it is not eliminated. This also brings up one more question which is very often answered wrongly in the literature. Is this covariant? We have started with integral root minus g d4x. Then we added to it an integral k root x d3x. This is our full action. Is this full action covariant? Well, the answer depends on what you mean by covariant. Now first let me give you an argument as to why it is not covariant in a nice sense. Everybody will agree that the A surface in Einstein's theory is not covariant. Now the A surface minus A surface prime we have shown is equal to this expression, which doesn't look covariant either. It only has spatial derivative. Therefore in that sense this cannot be covariant. But we started out with an integral k root x, so doesn't it look covariant? Let me do it in a slightly different way. Suppose you look at this k root x and you write it in the following form. Let me use this part. So you have an integral k per root of x d3x. I could have actually written it as This is on a boundary delta V. I could have actually written it as integral root minus g d4x of di of k ni. Let me explain what it means. If you take this and you just integrate, this is the divergence of a vector, this is a scalar, this is a vector, divergence of a vector, you will get a surface term, and that surface term is just this if ni is equal to 1 or plus or minus 1. So I can just put a plus or minus. But what have we done? What we have done is the following. You have some region V and it has a boundary delta V. You were originally given a vector field Ni just on the boundary. You didn't know what it is anywhere else. So this is a space-time, there is a region, and there is a surface is given to you and the normal Ni. Now I will choose some arbitrary vector field Ni defined everywhere in the space in such a way that it precisely matches with this Ni on this boundary. Inside I will take it to be arbitrary, I don't care. Then I can compute this quantity for that, making sure that this Ni matches with this Ni. So when I am integrating on the boundary, I will just get Ni which is 1 or minus 1, so I am not worried about the sign here. So just with that, these two things are equal. This is fine, there is no problem with that. I can extend it in any which way I like. But now see what has happened. You originally had an action which has r root minus g d4x integrated over a volume. This surface term I can explicitly write it as an integral over a volume of some quantity, which means just as I can add this to r root minus g, I could have taken just r and to r I could have added this. Now is that covariant? Well, it looks covariant. It is r plus nabla I of k ni, where k is a divergence of a vector field and ni is a vector field. So in that sense it is covariant. But at the same time, it is not a covariant quantity constructed out of metric and its derivatives alone. That is the point. We had to introduce an extra vector field in order to bring this covariance. So the price which we pay in order for this covariance is an introduction of an extra vector field. Now once you are willing to give me vector fields, I can make almost anything covariant. For example, if you take energy momentum tensor and you look at T00, and if I ask you whether this is covariant or not, this is the energy density, and if I ask you whether it's covariant, you will say, of course it's not covariant, it depends on what time coordinate you have chosen. If I change the coordinate, it will change. But I can write a quantity which is TAB UB, where this UA in a particular frame has 1, 0, 0. Now this quantity is perfectly a covariant object, but it uses an extra vector field. So if you have given an extra vector field, its numerical value will of course remain same in every frame, but that is no longer the 0, 0 component of a tensor, it's a scalar. So in the same kind of a way, if an extra vector field is given, you can write down expressions like this, which are manifestly covariant. And it is in this sense that the k root h is covariant. The more precise statement is that, well, it is generally covariant, but it is foliation dependent. So you choose a foliation, you choose an extra vector field which is assigned to that foliation with a lot of arbitrariness, and once you have done that much, then you can do this. So in fact, there isn't any great advantage in doing that compared to just dropping that surface term and working with the quadratic term. And you will get virtually the same kind of results most of the time. That is probably a good place to break now, and then we will come back again at 4. Yeah.
Yes, question. If you make this foliation dynamical,
can I make this foliation dynamical? Meaning what?
Meaning that this I is a dynamical field with its own equations of motion.
Oh, okay. I haven't thought about that. So you want to add another Lagrangian term or whatever for Ni as a vector field. Yeah, and then you think of this full theory as no, I haven't thought about that. So let me just give you a.
I think there is a comment involved that you cannot do this.
Well, I'm not sure whether you can or you cannot, but there is one issue here. There is a huge arbitrariness in Ni. You see, Ni for your purpose is specified only on this boundary. Okay? And you are going to extrapolate it into the volume. And I can do it in any way I like, in infinite number of ways. I mean, there are several vector fields which will match smoothly with this.
But if it satisfies the equation of motion, it would be only one.
Yeah, then the question arises as to whether there is even one which will satisfy that. And that will depend on what geometry you are choosing, etc. So that will bring about extra conditions on that. So I don't know the answer to that offhand. And but what is the purpose behind that?
No, to make the theory covariant.
No, the theory will not become covariant because of that.
Well, I mean, here there is a background if you want, which is...
Yes, there is a... So...
in your case, the background is dynamical, so it's...
No, because the moment you start varying Ni, you are back to square one. It is a vector field coupled to gravity with a very, very strange coupling. So all the variations which come from varying the metric, because then when you are starting to vary that with this as dynamical, there are all kinds of energy momentum tensor terms which will be contributed by that. And the variation of R root minus G will just come from the other piece. So you will be back to square one. No, I don't think that would work, but if there are other ideas like people have tried this in the concept of things like fluctuating membranes. So you have a normal vector field and you want to give dynamics so that it sort of fluctuates and things of that sort. But I thought maybe you refer to it in that context.
And the vector field would not be minimally coupled.
It will not be. It will be very non-minimally coupled. Yeah, it will even have a derivative coupling from the look of it. Yeah. Okay, so maybe we can come back at 4. Yeah. Okay, so I have a few more tips and tidbits of these things which I want to finish off, and after that we will move on to another subject. So I spent so much of time talking about the surface term, so let me write it down once again. It is up there, which uses this vector field Vc, which is minus 1 over G dB of GBC. And as I said, this is not quite a vector field because it is not a covariant 4-vector construct. Incidentally, this is a good time to clarify maybe one more misunderstanding which I have come across with people. So this is a bit of an aside, but it is relevant to this. Consider the following theorem, which says let us say ddx of di of vi on some volume is equal to integral on the boundary dd minus 1 x, where this is supposed to incorporate the root minus g or the proper kind of terms times ni vi. We all know this. Called Gauss theorem or Stokes theorem depending on the dimension. And people seem to think that this is a result applicable to vector fields. This is applicable to any n tuple of functions. This is just a thing in integration of calculus that you can take the boundaries and then integrate and verify for itself. Of course, then the result will depend on what coordinate system you use. So the things like these integrations and the surface terms, etc., has absolutely nothing to do with the transformation properties of these objects. They need not be vector. So sometimes there is a bit of a confusion that since it is not a vector, all these operations which we are doing is correct. They are correct because they only require the fact that these are n tuples which satisfies this. Now, but why am I concentrating so much on this, and what does it mean? Does it have a physical meaning? It turns out that it has a remarkably simple physical meaning, and that ties up with what we have been doing in the previous lecture. So let me try to show that. If you recall, in the earlier lectures we saw that there is a very generic structure which emerges near the horizon surface in any space-time, as long as it is what is called a non-extremal horizon. So you will have one sensible, maximally extended coordinate system like xt. In the case of short-scale black hole, for example, x and t will be the critical coordinates. In the case of flat space-time with Rindler horizon, these are the inertial coordinates. Then you analytically continue to the Euclidean sector. So I just put a T here. Once you do that, the corresponding Rindler coordinate or the type coordinates would be some small x and g times time or t. So we have done this several times in the previous lecture, so I won't repeat that. And this coordinate is periodic with a period 2 pi over g. Okay? What I want to do is that compute the integral of this, the surface term, on the horizon. So I take a solution which has a horizon, like if we are discussing Einstein's theory, you take a black hole solution, say short-scale black hole, and I want to compute what is the value of the surface term on the horizon. Now, evaluating things on the horizon is a bit tricky because all the metric coefficients are badly behaved. So what we will do is to take a surface very close to the horizon and then take the limit of it going to the horizon. So for example, I can take r is equal to 2m plus epsilon, compute everything and then let epsilon go into 0 and it will be a smooth limit. It is still better in Euclidean. In fact, I want to compute that surface term in Euclidean action. So I will work with a Euclidean metric. In the Euclidean metric, you know that all the region inside the horizon just collapses to this point. Okay. So what I want to do is to take a circle around the origin of radius, let us say epsilon, and compute this surface term on that. If I do that, I have done it for the whole class of horizons, I don't have to repeat it. And since it is finally I am going to take epsilon going to 0 limit, I can use these local coordinates here and I can set my metric to be just ds square, which is equal to minus kappa square, which is the surface gravity, x square, in Euclidean it is plus dte square, plus the spatial coordinates, which I will separate it as dx square, plus dx transverse square. It can be in d dimension, but if it is, for example, 4 dimension, then this is a 2-dimensional transverse plane. This is the metric. So let us compute what this quantity is going to be. What we are interested in is the integral over, let us say, the d minus 1. So in this particular case, it is d3x. The idea is extend to all the dimensions. Root h times the normal NC Vc. What is this? So this is going to be integral d3x. Let us first evaluate what is inside. Root h here is going to be just the metric on the induced surface. So the surface is x is equal to constant. So this dx square goes away. And I will assume that we have set up things so that this is Cartesian. So I have only the term coming from the G00. So you get kappa x, which is epsilon. Remember that we are computing it on a surface, x is equal to epsilon. Okay? So that is root h factor. Then MC is the normal to that surface. This is the normal in the x direction. Dx squared's coefficient is 1, so it is just 1 in any direction, so I don't have to worry. And I just have to write Vx, the x component of V. What is Vx? You go back to this. Vx is minus 1 upon G. G will be again kappa square x square, which is evaluated at x is equal to epsilon, so kappa square epsilon square. So in this I have dB of again kappa square epsilon square, it is this, then GBx. For this metric only the x component contributes and that is 1, so I only need an x derivative here. And kappa square just go away. So if I, of course, this is x square and then after derivative I have to put x is equal to epsilon. So this is what we have. This is minus integral d3x kappa epsilon here. And when you take the derivative of this is 2 times x, and that gives me a 2 over epsilon. So these epsilons also cancel out. So you get minus 2 kappa integral. What is this integral? We are on x equals constant surface. So there is a dt integral which is periodic. So the periodic gt goes to 2 pi. So this goes into 2 pi over kappa. Then you have an integral over the transverse coordinates. d minus 2. Here it will be dt. So again these two go away and you get minus 4 pi times the transverse area of the horizon. Epsilon has anyway disappeared, so I don't have to take epsilon going to 0 limit at all. Now this entire thing, this VC, comes from our Lagrangian, and usually the Lagrangian for Einstein's theory is written as 1 over 16 pi times r root minus g. Okay? So the actual Lagrangian has this divided by 16 pi. So the r root minus g upon 16 pi, which I never worried about, will give you a contribution on the surface, which is a very nice 1/4 of the area of the horizon. This is nothing but the entropy of that horizon. Okay, in Einstein's theory.
The sign is from the Euclidean.
Yeah, no, the sign is from the Euclidean. I was about to comment on that. What we are computing is the Euclidean action. So the probabilities in Euclidean action goes as e to the minus a Euclidean. But the probabilities in thermodynamic interpretation will go as e to the times the entropy. So the entropy should be negative of the Euclidean action. So the Euclidean action is minus 1/4 ahead, and that will become 1/4 of this. Now this is remarkable. I think you should stop and stare at it. What have we done? We started with Einstein's theory. So in Einstein's theory you had an action which is r root minus g. Then we said it has 2 parts. This is the equation. Then we had a surface term and we have a bulk term. First thing we did was to throw away the surface term, because we either cancel its variations by adding a k root h, or you just say that I don't care about it and I will just vary this. Then you get differential equations of the theory, the field equations of the theory. The field equations of the theory were never contributed by the surface term. This point is important, so let me actually show it to you the way the textbooks would derive it without any of this. In the textbook derivation, what one would be doing is to take this expression RAB GAB d4x and vary this. When you vary that, you will pick up 2 terms. You will first pick up d4x times, you will have an RAB delta of root minus g GAB. Okay? This comes from the first term. Then you will have an integral root minus g d4x GAB delta of RAB. Now, if I had asked you where the physics is contained in this, you would have probably thought the physics is contained in the curvature tensor or the Ricci tensor, and the variation of the Ricci tensor should tell us something. It does nothing of that kind. This RAB, this term, gives you the Einstein's equation. The variation of this, when you compute, you will get GAB delta GAB root minus g. This is what this term will lead to. This term, with all the variation of delta RAB, just becomes a total divergence. You compute it, you will find this is a divergence, and this is the term which you throw away. So this is the variation of the surface term which completely vanishes. And you pick up the entire Einstein's theory structure from varying root minus g delta GAB, keeping this almost constant. If I had said that let me treat RAB and GAB as independent variables and vary them and just vary metric, I would have got back exactly Einstein's equation. Okay? So this term does not contribute at all. And so I could have thrown away the surface term right at the beginning. Then you get the field equations. Then you solve the field equations. You get a solution with a horizon. Once you have got the solution with the horizon, you say, oh, well, there is this term which I threw away long back. Let me look at that. And you take that solution, plug it into that term which you threw away, and you get back something as important as the entropy of the horizon. This, I think, is a little bit mysterious and needs to be understood. And there is a way of understanding that which I want to explain. I am going to explain it qualitatively. I mean, there isn't much of a mathematical which is required. The way you think about it, or at least the way I think about it, is the following. You are starting with a theory which has principle of equivalence and general covariance. So what does this tell you? This tells you in a nutshell that A, the theory is geometrical and the spacetime is described by a metric tensor. So if I want to write down dynamical equations, these has to be dynamical equations for the metric tensor. If I want to write down an action functional, I have to write down an action functional for that. But just a second. The principle of general covariance tells you, on the other hand, that all observers are equal. So you could have done the physics with any observer. But one of the consequences of the geometrical nature of the theory is that there will be regions which are inaccessible to certain class of observers. This could be a region behind a Rindler horizon in flat spacetime. This could be a region where the metric is so badly curved that there is a black hole and there is a region which is not accessible to the outside observers. This is inevitable. Now you say the democracy of observers, that anyone has equal right to do physics, implies that there must be a way the person can accommodate the loss of information in a given spacetime. This is somewhat like renormalization group theory in particle physics. In a good particle physics theory, if I am calculating some scattering process at, let us say, 1 GeV, what is happening at 10 to the 14 GeV should not affect it, because I don't know the theory at 10 to the 14 GeV. So the coupling constants has to adjust themselves in such a way that this is taken care of. So now suppose I have a theory, geometrical theory, in which there is a black hole out there. I don't know what is going on inside the black hole. So if I am doing physics here, everything inside the black hole should be irrelevant to me. Of course it is irrelevant classically because nothing can come out. But that has to be true even as a quantum principle. And the quantum mechanics cares for the action functions. Quantum mechanics doesn't care about the classical equations, it cares for the action functional. So in the action functional there is a way of encoding the information which is lost inside the black hole. Now if you roughly think of the information which is lost there, is going to be the information which is the equivalent information content is what represented as the entropy of the black hole. Then the entropy and the surface behavior of the black hole should encode this information. The only way you can do that in a theory which has general covariance is to by force have a surface term in the action. That is precisely what we found. We found that if I want to write down a generally covariant equation which is at most second order in time, then the only choice I have is R root minus G, and that does have a surface term. And the reason the physics adjusts itself in order to have the surface term is because it knows that a different observers has to be able to accommodate the different levels of information they have by a boundary term. Just think about it, this is no more mysterious, at least in Euclidean sector is very apparent, compared to what we normally do when you set up initial conditions. Suppose I have a field and I am going to evolve it from t is equal to t1 forward. What does that mean? What it means is that I can forget everything below t is equal to t1. On that surface, I give you a data and then I can evolve it forward in time. So in the same sort of way, if there is an interior region of a black hole which I want to ignore, I should be able to give surface data on the surface of the black hole. So there are three important constraints on any action functional in a geometrical theory which obeys principle of equivalence and general covariance, and the equations of motion are not higher order compared to 2. That comes in a very complicated way. So that may not be apparent from what I have said, but these are the three conditions which comes in. First, there must be a surface term. If the action is generally covalent, it should have a surface term. Second, the surface term and the bulk term has to be related to each other in a holographic manner. That is again important because this answers, at least in my mind, the perennial question as to the degrees of freedom for which accounts for the black hole's entropy. Do they live on the surface of the black hole or do they live inside? Are they the content which is integrated out inside, or are they something which is happening at one Planck length around the surface? To my mind, this is irrelevant because if the surface term in the action and the bulk term in the action are related in a particular way, I can trade off one for the other. Whether I think of the bulk degrees of freedom or a surface degrees of freedom, the theory knows which is which and can translate back and forth. So surface term is nicer to deal with, so that is how we worked it out. And as you can see, the same way I could have got this entropy even from the quadratic term. It requires a lot more work because it is a derivative of that is what is appearing in the surface term, and since I know how to get it from the surface term, I can also obtain that. That is obvious from this math. But it is much nicer to think in terms of surface because that is an outside phenomenon. So the first is that there is a holographic relation between surface and boundary. Second is that there must be a surface term in the action functional. And the third is, when you evaluate this surface term, you must get back the entropy of the thing, because the entropy is related to the information which is lost. Now, if this is all correct, I mean all these conjectural interpretation of Einstein's theory is correct, it should hold for a much larger class of theories. So any theory which obeys principle of equivalence, principle of general covariance, and the equations of motion not being higher order compared to degree 2, in any such theory, this result should hold. The action must have a bulk term and a surface term. They must be holographically related, and the surface term should give entropy. This indeed happens. So I wanted to describe that to you, which would be the next part. Okay.
Quickly ask the question: what happens to the given smoking
Counter time?
term when you try to calculate?
Yeah. If you compute this quantity for short-scale kind of a metric, the short-scale kind of metric has a parameterization where the shift vector vanishes. Therefore, these two are identical. So in fact, most of the computations in the literature, you will find they just calculate k root h and obtain the entropy. And the reason it works there is because you are using a foliation in which that vanishes. In any space-time, you can choose coordinates in such a way that the shift vector vanishes. So there always exists a foliation in an arbitrary space-time in which you can make these two things match. But it is not a generally true statement, and it is certainly not a covariant statement. So let me now go to the class of examples in which all these results hold, and where the entropic interpretation of the surface term does come. So, since I have wiped everything out, let me just start by writing one or two relations which we need. The first was this Lagrangian, I wrote as Q, A, B, C, D, or A, B, C, D. This is the class of theories which we are going to look at. And I told you that in all these theories, there is, if I put a root minus G, all these theories, this can be expressed as root minus G times a L quadratic plus an L surface. This I had already shown you. That is straightforward mathematics. Now I want to list the other properties of these theories. These are all provable, but I don't think you gain much by actually working through the mathematics. So I can list those properties. But in particular, I want to concentrate on the class of theories and the class of Qs which you have. So to do that, let us again go back to the L Einstein helper. which we said can be written as, I'll use a slightly different notation. I think I use even numbers on top. 1, 2, 3, 4, or 1, 3, 2, 4. This is just a fancy notation which makes life easy. This you should think of as some x2. Okay? Think of this as a letter, one alphabet. 2 is one alphabet, A or B or whatever. But it makes the generalization very easy. Now the next thing which you would do, arising out of this, is another Lagrangian which I can write down, where I take 2 copies of R and I multiply it by a delta. So here I will have 2, 4, 6, 8, 1, 3, 5, 7. Assuming I don't want to count it. So this is going to be 1, 3, 2, 4, and 5, 7, 6, 8. Okay. So again think of it as labeled A, B, C, D, I, J, K, L and the corresponding things. So I have just taken 2 copies of the curvature tensor and multiplied it by the determinant tensor. This Lagrangian is known as the Gauss-Bonnet Lagrangian. The integral of that gives you the Gauss-Bonnet term. Now this quantity has to be completely anti-symmetric in all the indices. Okay? So the next one which I would write down would be what I will call L3. We'll have a delta which has 2, 4, 6, 8, then 10, 12, etc. and 3R. This is 0 in 4D. For obvious reasons, because I can only have at most antisymmetric terms up to 4. Okay? And in fact, we know that even the antisymmetric tensor in 4 dimension is unique. It is just an epsilon. That means that this is what I have written down here is just a double dual of the curvature tensor. That is, this can be traded off for 2 epsilons with suitable numerical factor. So one epsilon will contract on this, another epsilon will contract on this, and then they will contract on each other. Okay? So you could have thought of this as taking any one curvature tensor, then taking 2 of those indices and using an epsilon to find its dual, then use another epsilon to take the dual of the other 2. So you take the double dual of a Riemann-Christoffel tensor and multiply by another Riemann-Christoffel tensor. That is another way of thinking of this Gauss-Bonnet term. So in 4 dimension, if you want structures like this, you stop here. But in higher dimension, you could have gone on like this. And the mth order term will have a structure like this. This is known as the mth order Lanczos-Lovelock Lagrangian. That will have delta, again 1, 3, etc. all the way to, let us say, 2k minus 1. And here you start 2, 4, you go all the way to 2k. Then you have the Riemann-Christoffel tensors which are 2, 4, 1, 3 times the final one will be R, assuming I got my combinatorics right, 2k minus 2, 2k with 2k minus 3 and 2k minus 1. So these are the copies which you have. And this k is like 2m. This k will be 2m, where m is the mth order Lagrangian. So you can construct this, and they also has a nice interpretation in terms of curvature 2 forms. It is just a Wurtz product of any number of curvature 2 forms. And these Lagrangians are called the Lovelock Lagrangian. They have the following properties. First of all, if you try to write it in this form, it can be done easily, because I just have to remove one R, and then this Q is going to be, suppose there are k r curvature tensors in the expression. I remove one, the Q will have k minus 1 curvature tensors. And it is a homogeneous function of degree k minus 1 in these curvature tensors. And that expression can be used to define a surface term, for example. And the surface term and the bulk term and everything. The remarkable feature about these theories is that when you work out the field equations of this theory, which is given in the notes, the field equations become algebraic in these Qs. That is, it is a Q plus some extra terms which involves L, etc. is equal to 0. That is what it happens. When you look at that, each of these contains the right curvature tensor. Curvature tensor contains second derivatives of the metric tensor, no higher. So the final field equations does not involve, for example, third derivatives of the metric tensor. This would not be the case, for example, if you take Lagrangian like RAB. Okay? If you take just the quadratic part of this particular combination which I have written down here, this Gauss-Bonnet, it will have an RAB, it will have an R square, it will have an RABCD. But they will appear with the coefficients in precisely of that kind, that finally when you write down the field equation, the field equations involve only second derivative of the metric tensor and nothing higher. And that will not happen except when you do it in this particular form. And for all these cases, you can also prove that the divergence of QABCD vanishes. That is the second feature. And they are also all holographic in exactly the same way Einstein's theory is. Okay, that relation also you can prove. So, final thing which you need to do is to look for black hole or any solution with horizon in that. So for Lovelock theories, people have investigated black hole solutions and people have determined what is the entropy of these black holes are. These entropies are not 1/4 of the area. That is a special property of Einstein's theory. In general, the entropy is not 1/4 of the area. In fact, that is also an interesting thing to keep in mind. Given a metric, if you look at the periodicity of the Euclidean time and if the period is fixed, from there you can assign it a temperature. And if the metric in any theory has a Rindler approximation close to the boundary, then in all those theories you will find that the temperature is just kappa over 2 pi, where kappa is the surface current. That is a universal statement. But you cannot make a similar statement about the entropy. You might have thought that there must be a simple relation, but there isn't, because the entropy, even in Einstein's theory, came about because we had to write some TdS equal to E kind of an equation and integrate that and make an interpretation that E is equal to M and that sort of a thing. So some amount of dynamics has gone into it. Another way of thinking about this is, if you wanted to compute entropy from the action functional, I had to take the surface term and compute it. And that surface term was very specific to R root minus E. That is where I did this computation. But for any of the theories, the generalized theories like Lovelock theories, there is a way of defining the entropy. What you do is the following. You think of that black hole solution and you throw in a test particle into it. You know that the mass is going to change by delta M. Then you ask how much the other parameters change, and then you write down this T you can fix from the Euclidean periodicity. So you know TdS equals dm. S is the only unknown. T is known as a function of M, and you can integrate. You can integrate that expression and obtain an expression for the entropy. There is a rather remarkable limit for this Lovelock, which I don't have time to derive, that the entropy of a black hole or a horizon, Rindler-like horizon, in the mth order Lovelock theory is just the Lagrangian of the m-1th order integrated over the surface. Okay, so you just take away one r and you integrate that, and then you get back the entropy, which is of course true in Einstein's theory. Like if you look at the entropy in Gauss-Bonnet theory, it is the 1/4 of area which you get from the standard Einstein plus the integral of Ricci scalar over the surface of the black hole. That is the entropy in Gauss-Bonnet theory. And in Einstein's theory, the lowest order, if you remove that r, is a constant. So it's an integral over the surface times a constant. Of course, the constants has to be fixed by some normalization convention, and you usually fix in such a way that to the lowest order you get 1/4 of this, which is that 1/16 by normalization. So you can compute this entropy, and as I said, even at Gauss-Bonnet level, the entropy is not 1/4 of the area, but it is 1/4 of the area plus a correction term. What is remarkable is that if you look at the boundary term of this theory with this horrible Lagrangian, and you pick up what is that the boundary term which comes from here, which will have one Q and a gamma. Q will now involve curvature. Like if you take the mth order Lovelock theory, Q will have m-1 products of the curvature tensor and one gamma. It is non-covariant. You compute this quantity on the horizon and you get back precisely the word center. Okay. So the idea that boundary terms in actions are something which you can throw away, I find it very, very difficult to accept. And they contain a hell of a lot of physics. And I have tried to argue, at least give you a qualitative interpretation as to why it does that. It depends on principle of equivalence, principle of general covariance, and the fact that when there are horizons and some information is lost, which implies that these three things has to tie together. And that is precisely what happens in all these theories. And so in that sense it is not a mystery. But you have to understand it from that perspective. Okay, so that is basically all that I wanted to do about the Lovelock extension and the boundary term. Now just for the sake of complete...
So now I think you said it, but you were too fast for me. So if I now take in 4D, I add the Gauss-Bonnet term, then that's basically a surface.
Yeah, in 4D it doesn't contribute, but you take a 5-dimensional theory.
Yeah, but in 4D, would it not change then if you then integrate the surface term, would it not then change?
No, because this is a surface we are talking about, right? Because there is already a surface term, but if you are picking out the surface term out of it, that will vanish in any compact boundary. But if you take the minimum 5D, there are genuine nice black hole solutions to Gauss-Bonnet theory, and you can compute their entropy and you will get this result. Yeah. Okay. Now just for the sake of completeness and also to connect it with this issue of momenta which I mentioned, I want to do explicitly the variation of the R root minus the action, which I have not done at all. I mean, I went very close to it, but I didn't work it out. I won't do it on the board, but I will just quote the results. But there are a few points to note on that, which I will stress. So the first point is that if you know the boundary term in the theory, you can determine the momenta. Okay? So I gave you a classical mechanics example, but that is a little too trivial. And I don't know how many of you have done it for electrodynamics. So let me just do it for you in electrodynamics. It is quite interesting. So if you take action in electromagnetism, you have a theory which is, okay, in some notation it is 1/16 pi again. I think it is 1/16 pi, yes. Fik, flat space-time, Lorentz invariant electrodynamics. Fik, d4x. Now you want to study the variation of this. So if you look at the variation, delta Em, let's see what we will get. You are going to vary this. There are already two factors that will give you a factor 2. And then inside I am going to vary Ai, that is antisymmetric in Ai, another factor 2. So I will pick up first of all a factor 4, so I can write 1/4 pi. Then I need to retain only one of them, so let me keep Fik. Then in this I will have di of, let us say, delta Ak, d4x. I hope this part is obvious. Okay, so it's not too fast. Then this, of course, you will write as delta Ak, and you want to take out the total divergence term out of that. That is going to be minus 1/4 pi integral d4x di of Fik delta Ak. Then of course you have a term dIFik delta ak, which is the Euler term or Euler-Lagrange term, and that term is on shell it goes away. I'm only interested in picking out the canonical momenta, so that term I'm not even writing, which is the term you will write in normal textbooks. You would throw away this term and retain that term, but I want to retain this term. So what does this term give me? So this term is going to give me, I can write it as F. Well, I don't need to, F I can. Okay, so this I'm going to integrate, and let me concentrate on a t equals constant surface. So first of all, this is going to give me only a surface term, and on the t equals constant surface, this will give me 1 upon 4 pi integral over d3x F, I'm on the t is equal to constant surface, so there is only the 0 index which contributes. F0k delta ak. The first point you note is that because of the antisymmetry of F, only the spatial parts contribute. This is F0 alpha and this is A alpha. And F0 alpha, you know, is an electric field. So this is proportional to integral d3x, except for constants, E dot delta A. This is a nice result. It is rather unfortunate that it is not often discussed in textbooks. What it tells you is that if you are looking at electromagnetic action and you think of the Q's of the electromagnetic theory as AIs, the vector potential, then the P's of the theory are actually electric fields. Okay. It is also clear from this picture that when you look at this, that there is no analog of the canonical momenta corresponding to A0. These are the canonical momenta analogous to the vector A coming from this. The A0 has no momenta associated with it. This is well known. I mean, this has to do with the fact that the time derivative of A0 never appears in the Lagrangian. Because if you look at this Lagrangian, the time derivatives can appear only through this zero term in this, and that zero term never acts on a zero term because of antisymmetry. So only the time derivatives of the spatial part of the vector potential appears in Einstein. This is E square minus B square, and E has a dA by dt while B doesn't have anything. So it is only dA by dt which appears. So therefore, this is related to all kinds of things like how to do the gauge fixing and the gauge non-propagating modes, etc. When you try to quantize electromagnetism, it creates mess. But it is already seen here that you have canonical momenta only associated with it. So it is not guaranteed that when you vary your action, you will pick up canonical momenta for every degree of freedom. You might have written down some degree of freedom, but all of them will not happen. For example, in the theory of gravity, G00 and G0 alpha will not have canonical momenta. It is only G alpha beta which will have canonical momenta. For the same reason, when you work through the mathematics for that, they will just disappear. Now there are also a few more interesting things. If this is what you are going to pick up, you can ask what has to be fixed at the endpoints. There you have to be a little bit careful, because if divergence of E holds on the shell, then you don't have to actually think of delta E, arbitrary delta E. You only want to fix it subject to the condition that the divergence of that can be eliminated. That means only curl of E need to be fixed. So in a very genuine sense, in electromagnetism, the Q's are the magnetic fields and the E's are the momenta, the P's are the electric field. So there is a very nice duality between these two, and this is how you pick up what is the canonical momenta in a theory. Now we can try to do the same thing in Einstein's gravity. It's a holy mess, but I will give you the answer for that. And that is important when you think of this as a momentum space description of the theory, etc. Okay, so how do we do it in Einstein's theory? Yeah, let me try to write it here itself. So what you want to do is to compute, let us say, the variation of root minus g L quadratic. Because we know that the quadratic part alone will give you the necessary equations of motion. But it is nicer to do this by calculating root minus g of r, which I will write as GAB RAB. This is because you can look this up in textbooks. Then minus delta of the L surface, which you have to work out, unfortunately. So this is known, and I will just write down the final answers in both these cases. When you do this, you pick up the usual term, which is capital GAB times delta GAB, which is the standard Einstein term times root minus g. Then I told you the term which you throw away, which is root minus g, except that we are not going to throw it away. Root minus g GAB delta RAB. Then I have minus delta L surface. Okay? So this is what you want, and there are these two extra pieces which has to be computed, and we have to see what emerges out of it. That would give you delta of L quadratic. We don't expect any surprises. For example, when you compute this, you better get back something times delta GAB. No derivatives of GAB should appear because we are varying a quadratic action. And that is precisely what will happen. So I'll write down the expressions for both of them. First, the expression for delta RIB. Root minus g GAB delta RAB. This term will turn out to be twice some dA, or rather in my notation dC, root minus g GBK QCDAK delta of gamma ABB. So this is the standard climb, and I have written it in terms of Q for convenience. So, and this can be expressed entirely in terms of the derivatives of the variation of the derivatives of the metric. So the standard climb is that this is the surface term which we throw away. And as I have told you, you can already see why the standard climb has a problem, because it involves the variations of the derivatives of the metric. In particular, it involves the variations of the derivatives of the metric normal to the surface. And those are taboo. Once the metric is fixed, the derivatives on the surface is fixed, but not the one which is across. So you have this term in this. But the way it gets out when you calculate the surface is that you go and compute what exactly this delta L surface is. Both are straightforward computation, it's just a bit tedious. That you will find is given by dC of exactly this term. It is 2 root minus g GBK Q CDAK delta of gamma A dt. Then you pick up a new term, which is interesting and which is not often explicitly shown in literature, which is plus square root of minus g, capital M. I'll write it down, then describe what it is. CLM delta GLM, where this quantity is defined as M C LM happens to be gamma CLM minus gamma L, let us say II delta CM minus half GLM VC. VC is that, or surface area. So this is what you find. You find that delta RAB is this and delta L surface is this, and if you recall, what we needed was the difference between these two. Okay? When you take the difference between these two, which will give you this delta root minus g chord, the delta of root minus g L squared, you will find is equal to root minus g GAB delta GAB and we defined it as this minus this, so that will give you this extra term which is minus BC root minus G MC LM delta G. It's definitely worth arriving for students at least once. So what does this tell you? This tells you that you can start with this L quadratic and just vary it. When you vary it, you pick up two terms. The first term is this, which is GAB times delta GAB. Then you get a second term, which is a total divergence. Now when you integrate it to get the action, when you do the integral over this, what you are going to get is this term on the surface. And it involves only delta GLM on the surface, multiplied by these quantities. Therefore, it is a genuine, nice variational principle. And what is more, as a bonus, we can identify these as the momenta associated with the metric. So the expression for momenta is a little bit complicated. But for example, if you are looking at a particular surface, like if you dot it with an NC, where NC is zero component, but you can take a zero component of this and dot this out. So the canonical momenta, which is conjugate to the metric, can be read off, and that is what this quantity is. There is a much nicer way of thinking about this, which will play a role in our last lecture. I told you that there is this L quadratic. Now this L quadratic is of course quadratic in the first derivatives of the metric. So in principle you can write it as some 1/4, some M, ABC, IJK, dA of GBC, dI of GJK. Right? The quadratic expression is usually written as products of gammas. All that I am telling you to do is to take these gammas, expand it in terms of the first derivatives of the metric, and work through the algebra. Can be done. And I think I have explicitly given the expression in the notes for this M. And these M's are built out of metric tensors. So each of these M is a sum of a set of terms. Each term has 3 metric tensors in them, which essentially tells you how you can contract these in different ways in a particular order. Okay? So this is the structure which you have for L quadratic, which means that your canonical momentum which you would have thought of is dl squared with respect to d of, let us say, di gjk will just turn out to be something like half m abc ijk dA of gbc. If you work this through, you will find that this is identical to this commutator. You will find that this is equal to m I j k. One thing you can immediately verify, this is first order in the derivatives of the metric. Each of these are first order in the derivatives of metric, which is what you would expect. It is like queued off, so to speak. So there is a way in which you can vary the action, and when you vary this, you pick up terms from which you can read off the momenta, and it is these momenta which you keep fixed when you are looking at the variation of R root minus g. You can also write down the corresponding formula for that. See, all this we did with quadratic. If I had looked at root minus gr, okay, then what I would have got is that there it is better to use covariant indices GAB delta GAB. Then you would have found that the extra term is minus DC GIK delta of root minus G MIKC. Sorry, MCIK. Just to summarize again, if you vary R root minus B, you pick up this term which you want, then you get a surface term, and that surface term will involve delta of this quantity, and these quantities involve first derivatives of the metric. Therefore, the surface term will involve variation in the first derivatives of metric. But this I have identified as the canonical momentum of the theory. I identified that by looking at the variation of the quadratic part of the action and computing what it is. If I do the variation of the quadratic part of the action, just as we did the variation of the quadratic part of the electromagnetic action, Fik, on shell, when you do on shell, this will go away. And the surface term will have this delta GLM, and from that I can read out what these are. So these are my canonical momenta, just as we found electric field to be the canonical momenta in electrodynamics. So if I keep those canonical momenta fixed when I am varying, then I pick up the Einstein's equation out of it. This is why this R root minus D is a momentum space action principle, which is not something which is often appreciated. That's why I went through the whole analysis to write down both of them. In the coordinate space, you have L quadratic. In the momentum space, you have root minus GR. They differ by a surface term, and everything else will work out properly when you do this analysis. Okay? Fine. So this is essentially all that I wanted to cover as regards the action principles here. And now I want to go further, and I wanted to talk about a little bit on spin tube fields and their connection with gravity. So shall I do it now, or should I start in the next lecture? Or well, I never could figure out how many hours it goes through this. 1 hour after coffee. So what do you think?
For me, it's okay. I mean, if you think that that you can finish in the next lecture, what you want to say, then
well, I'm anyway behind schedule, so that is not an issue. There is this famous comment by John Wheeler that the purpose of a course is not to cover a syllabus, but to uncover it. Okay, so in that sense, it is all right. Okay, so maybe I can make some preliminary comments and then skip the mathematics to the next lecture. So let me do that. Okay. So the next topic which I wanted to take up and discuss is the concept of so-called graviton or a spin tube field. And this is something which is very popular with particle physics, so it is well worth knowing even if you are a general like it and may not have a sympathy for a particle physics approach. The idea is, if you want to write down a Lagrangian for a theory, you often look at what kind of solutions you are actually interested in And then you see what kind of Lagrangians or actions will lead to that. I mean, that is not the way you finally present it in the textbook, but that is the way the thinking process works. So let us try to start with some simple examples. Suppose you are looking at a scalar field, again flat space-time special relativistic physics. Then you can have an equation which is of this form. So J is the source, phi is the field, and box phi is equal to J. Linear equation, and then you can solve for it and look at solutions, etc. etc. Now, what kind of action from which this can come out? Or in fact, even if you simplify it even further, if you don't even have this J can come from just a J phi coupling. Where does your box phi comes from? We all know that. This comes from an action where I could have written it as, let us say, minus half integral d4x di phi di phi. No problems there. And then, of course, this is the free field action. Then you add to it that J phi term. That I am not so much concerned about. Now let us try to do the same thing for a vector field. So I have a vector field Vi whose source is, let us say, Ji. I want this equation to hold. What is the simplest action you would write down? Now, vector field is nothing but 4 scalar fields because each component satisfies that box phi. So I could have written down an equation here, action here, which is again minus half integral d4x di of, let us say, Vj di of Vj. Okay. Now wait a second. This is electromagnetism. This V is AI and this is the current and it is in some particular gate, etc. etc. And we don't write down this action. We write down Fik. And there is a gauge invariance in the gate. Where does all that come from? Now can you discover that? So I want to give you a motivational argument as to how you can discover that, because it's going to be useful when we go to the next stage and look at the graviton, which is a spin 2 field. The point is, if you look at this, I'm using a signature minus plus plus plus, and the lowest order term which I have is going to have a minus phi dot square term. With this extra minus sign, it becomes positive. So this will have a structure which is integral d4x half phi dot square plus 10 extra terms. Now you look at this. The time derivative terms are coming from this, but Lorentz invariance implies that the placement of integers has to be like this. Now you find you are in a trouble. If I arrange things in such a way here that one of them, here I have arranged it in such a way that the spatial terms has plus sign, the other one will have a minus sign. Because when you look at this, this is going to lead to a structure which has a V0 dot square with one sign minus V dot square. So you cannot have both kinetic energy terms having the right sign. So there will be propagating, and if you compute the energy for this system, the energy, if the kinetic energy flips, when things are changing with time, that is going to contribute to the kinetic energy and that will have the wrong sign. So you cannot have all the modes in the theory being physical modes carrying positive energy. So if you write down this Lagrangian, you run into trouble. So what do you want to do? What you want to do is, you want to have a symmetry in the theory which will allow me to eliminate at least 1 degree of freedom. There is 1 degree of freedom which is giving me trouble. The others I can set the sign in such a way that it is fine. So I need to be able to eliminate 1 degree of freedom. Yeah.
So here the problem comes indeed when you couple both kinds of fields.
That's correct.
So the solution would be try to decouple. Decouple this ghost or whatever.
Yeah, sure, you can do that, but there's a much simpler solution. The simpler solution is to eliminate that degree of freedom. Okay.
In other theories where there is this kind of phenomena.
Okay, it may not work and you may have to do something else. But in this particular theory, it is a lot easier just to eliminate that degree of freedom and be done with it. So how do you eliminate? You say that I want an invariance which has at least 1 degree of freedom. So 1 degree of freedom could be Vi going to Vi plus di of some function. So you think of a theory, a vector field theory, where you say I want this in a particular gauge, but I want my action to have invariance under this. Okay? Then I'll try to construct that action in a particular way. It's just electromagnetism, but I'll try to construct that action in a particular way in the next lecture to make some things obvious. So you will have it. Now let us go to the next step. Suppose I want a theory for a field which is second rank symmetric field, which has, let us say, Jij as the source. So again, the naive action you would write down will be minus half integral d4x dA of Hij dA of Hij. Again, same problem. And you will find now that there are 4 degrees of freedom, H0, 0 and H0 alpha, which has problem, and H alpha beta can be made one. Okay? So you again need to worry about a way of eliminating at least 4 degrees of freedom out of this. Right? Now in order to do that, you want to have a generalization of exactly this kind of a field. And here you use the scalar, now you use a vector. So you say that I want a theory in which Hij going to Hij plus di of some psi j plus dj of psi I is a symmetry. This is a very natural generalization of this. So the moment you do that, you again want to go back and ask what kind of action I can write down which is invariant under this. So the reason I want to do electromagnetism differently is to orient towards how to do that. Because here the maths is very easy, and you write down the most general action, impose the gauge invariant, you will get back electromagnetism, Fik, plus a Chern-Simons term which you throw away. Now here when you do that, you get a much more complicated expression, but this principle uniquely fixes the form of the Lagrangian, except for surface terms, which we want to come back to, but right now it doesn't matter. You can make a particular choice of the Lagrangian and you will get a quadratic expression here. Then we want to ask, if this symmetry is maintained in the theory, what constraints does that put into the theory? In electromagnetism, there is an interesting constraint it puts, namely that the field equations will have, something like this going as Jk. But the field equations, I could have written it down not in terms of Fik, which makes things very obvious, but if I have written down in terms of Ai, I will have a complicated field equation here. But it satisfies the identity that decay of that is 0. So it can be coupled only to a Ji which satisfies that condition. When I wrote down this equation, I didn't say that. I just wrote down some Ji and I said I can couple Ji, Ai. But then if I want to eliminate the bad degrees of freedom by a gauge transformation, then the only source to which it can couple to when the equations of motion are satisfied is a source which is conserved. Now you go back and do the same thing here, and you will discover that there is a similar constraint on the theory which you cannot bypass. It is imposed on you, which says that di of dAp or di of whatever is on the right hand side, Jik, should be 0. And this poses all kinds of problems which we will discuss in the next lecture. And so I will try to derive this, or at least indicate how this is derived, and then I will work out what its consequences are and make a few comments and comparison between electromagnetism and distinctive field. Okay. Then whatever remaining time I have, I will have some comments on the general structure of the Einstein's equation and the electrodynamics in a weakly curved spacetime. There are some interesting results. Yeah.
So I have a comment.
Yeah.
There is a difference between the vector and the tensor, which is that to the tensor you can also add something like eta ij with a scalar, right? So I mean, indeed, you wonder about the most general kind of gauge symmetry you can have, you should also try to
No,
do that.
actually not, because this is done in special relativity with Lorentz group kind of a structure in mind. Then you would like your fields to transform under an irreducible representation of the Lorentz group. So in fact, you don't add, you subtract. You make sure that the vectorial and scalar degrees of freedom of the second rank trigonometric tensor is taken out. And you have only propagating modes which actually carry spin 2.
Yes.
In principle, you can have a composite object. But I'm trying to distinguish between things in some very nice way. So if you want to describe a spin 2 graviton, you don't want a scalar degree of freedom.
No, I mean the scalar can be, so in the gauge transformation that you propose,
This one?
yes,
Yes.
you could also add a new, like,
Eta ij phi. Yeah,
and this would take away a scalar part of the gravity.
yeah, but you don't have to do that. What I'm saying is that with just this, I can eliminate all the unphysical degrees of freedom. So I don't need that.
You don't need it. But
I don't need that.
Okay, my point is that then if I impose that the vector is transverse and you add this, you go back to unimodular gravity, which is very close to general relativity.
No, it is not, because it breaks general covariance.
It breaks general covariance.
Yeah. So I think it is very far away from general relativity.
As far as the equations of motion are concerned, not.
No, not really. It gets you the trace-free parts of the equation.
Yes.
In fact, we had a debate on a different occasion about this. The point is that unimodular theory, if you think of it very strictly, prevents you from Cartesian coordinates to spherical polar coordinates. I think that is bad. So that's a very small, yeah, I see your point. I mean, you can eliminate other degrees of freedom in the graviton and then restrict it further with the extra degrees of freedom. But I don't want to do that, because for me, general covariance is sacred. So the theory which I am going to build will lead to general covariance. Yeah. Any other comments?